Welcome learners. This is semester 1 statistics paper 1 descriptive statistics and probability. In this video lecture we are going to discuss addition theorem on probability. The learning objective is some basic theorems on probability, addition theorem on probability for 2 events, 3 events and for n events. Okay, before going to prove the theorems, we just recall some basic things. In tossing a coin, we have two outcomes, namely H and T, head and tail. The probability of getting head is 1 by 2 and probability of getting tail is 1 by 2. Total probability of S must be equal to 1, that is 1 by 2 plus 1 by 2. The probability added to all events. This is equal to 1, and in this example probability of H bar is probability of S minus probability of H, that is 1 minus 1 by 2, that is equal to 1 by 2. We can write this probability of H bar as total probability minus probability of getting head, that is nothing but 1 by 2. Similarly, in rolling a die experiment, we have the probability of getting 1, 2, 3, 4, 5, 6 are same, that is 1 by 6. There are total 6 possibilities, 1 is favorable or 2 is 1 favorable. So these are the probabilities of getting phases 1 to up to 6, and probability of S is 1 here. Total, this is sum of all mutually exclusive events. Here also S is sum of mutually exclusive events. Here we can write this total as union of the H and T. That is, by axiomatic definition of probability, this probability of union of H and T is probability of H plus probability of tail. So here also probability of union of all 6 events must be equal to summation of all these 6 events. So probability of not getting 1 is 1 minus probability of S minus probability of 1, that is 1 minus 1 by 6, that is equal to 5 by 6. We are also recollect the distributive law on unions, that is A union B intersection C can be written as A union B intersection A union C. Similarly, A intersection B union C can be written as A intersection B union A intersection C. This is union of these two events, A intersection B, A intersection C. We can also know this. This is the distributive law on unions. Next, theorem 1 is the probability of impossible event phi is 0. That is, probability of phi is equal to 0. Since probability of S union phi is equal to S and S intersection phi, the intersection of phi is phi. And from the equation 1, taking probability on both sides, probability of S union phi is equal to probability of S. This is equal to, this probability of S union phi can be written as probability of S plus probability of phi, because by axiomatic definition of probability, probability of union I is equal to 1 to n ai must be equal to summation I is equal to 1 to n probability of ai. So this probability of phi is 1 minus probability of S, that is equal to probability of phi is equal to 1 minus probability of S is equal to 1, it is equal to 0, since probability of S is equal to 1. This theorem 2, probability of A bar must be equal to 1 minus probability of A. The probability of the complement of an event A is given by probability of A bar is equal to 1 minus probability of A. We know that A union A bar is equal to S. This is total probability. And A intersection A bar is equal to 5. There is no common elements to A and A bar. So this is 5. And taking probability on both sides for this expression, probability of A union A bar is equal to probability of S. That implies we can write this as probability of A plus probability of A bar is equal to 1, since A and A bar are mutually exclusive events. There is no common elements in A and A bar. So probability of A plus probability of A bar is equal to 1 by axiomatic definition of probability. From this, probability of A bar is equal to 1 minus probability of A. Next one is, for any two events A and B defined on a sample space S, probability of A bar intersection B is equal to probability of B minus probability of A intersection B. We can prove this theorem by using Venn diagrams. Look here, this is A and this is B. Here the vertical lines is A union A intersection B. This is A intersection B. And the horizontal lines is A bar. There is no A here, only B. A bar intersection B. Here we have A intersection B. A union B, this is expressed as two disjoint events A and A bar intersection B. This is A and this is A bar intersection B. Okay, this is A intersection B and this is A bar intersection B. Consider the Venn diagram. From Venn diagram, it can be seen that B is equal to, we have seen A bar intersection B union A intersection B. B is summation of these two events, union of these two events. Taking probability on both sides, since these two are mutually exclusive events, we can write this union instead of union we can write plus. Probability of B is equal to probability of A bar intersection B plus probability of A union B, since these two are mutually disjoint. There is no common element for A bar intersection B and A intersection B. So from this, probability of A bar intersection B is equal to probability of B minus probability of A intersection B. Hence the proof. Now addition theorem on probability for two events. For any two events A and B defined on a sample space S, probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. Again, consider Venn diagram. Here A and A bar intersection B are disjoint. Look here, this is A and this part, the vertical lines part is A bar intersection B. There is no common elements for A and A bar intersection B. You observe that A and A bar intersection B are disjoint. Therefore, A union B is equal to A union A bar intersection B, since these two are disjoint. This implies taking probability on both sides, probability of A union B is equal to probability of A union probability of A bar intersection B. Since these two are disjoint, we can express this as A probability of A plus probability of A bar intersection B. Here, to this expression, adding and subtracting probability of A intersection B. Here, this is the expression. adding probability of A intersection B minus probability of A intersection B. Here, take these two common. We know that this is A bar intersection B and A intersection B are disjoint, and the union of these two gives B. Therefore, instead of probability of A bar intersection B plus probability of A intersection B, we can write probability of B. We have seen this in the previous theorem. So, probability of A, this is probability of A, this is probability of B minus probability of A intersection B. So, we can express probability of A union B as summation of these two terms and minus of intersection of two terms. So, hence the proof. Let us look at the addition theorem for three events. For any three events A, B and C depend on a sample space S, probability of A union B union C is equal to probability of A plus probability of B plus probability of C minus probability of A intersection B minus probability of A intersection C minus probability of B intersection C plus probability of A intersection B intersection C. We prove this theorem by using the distributive property on unions. Consider probability of A union B union C. Keep a bracket here. Take this B union C as one event. So this is A and this is another event. This is the first event. This is the another event. From probability of addition theorem on probability for two events, we have this is one event, this is second event. We can write this as summation of this single terms union minus summation of these two terms minus intersection of these two terms. So this is probability of A and this is probability of B minus probability of A intersection B. Instead of B we have B union C. So this is first term, second term, first term, second term. Probability of A, this is again apply probability of A union B addition theorem on two events. Instead of probability of B union C, we can write probability of B plus probability of C minus probability of B intersection C, and this is we can write this A intersection B union C as A intersection B union A intersection C. We have seen in the first slide itself. This is distributive property of union of sets. Simplify this: probability of A, probability of B, probability of C, probability of B intersection C. Here again, this is union of two terms. Apply probability of addition theorem on two events for this expression. This is A, this is B. We know that probability of A plus probability of B minus probability of A intersection B. So take minus inside the bracket minus probability of A intersection B minus probability of A intersection C minus into minus plus. We can write this is the intersection of three events A intersection B intersection C. So this can be written as probability of A intersection B intersection C. So we have probability of A union B union C is equal to addition of three single terms minus intersection of three double terms plus intersection of three terms. So this is addition theorem on probability for three events. Now let us discuss the addition theorem on probability for n events. For n events a1, a2, an, we have probability of union of I is equal to 1 to n, ai is equal to summation I is equal to 1 to n, probability of ai minus double summation means this is double two terms, probability of ai intersection aj 1 is less than I, less than or equal to j, less than or equal to n, plus this is summation of 3 terms, intersection terms, minus so on. The last term is minus 1 power n minus 1. Look here, this is the last term. Here the sum, this is decided by, here we have 3 terms, minus 1 power 3 minus 1, 2, minus 1 into minus 1 becomes plus. Here in case of 2 terms, we have minus 1 power 2 minus 1, minus 1 power minus 1, minus 1 remains. So this is alternatively changing. So this is probability of A1 intersection A2 intersection AN. This theorem can be proved by mathematical induction. We know that in mathematical induction we prove for 2 terms and we prove for r terms. We assume that it is true for r terms and we prove it for r plus 1 terms, and hence it is true for all positive integers of n. And for 2 events A1 and A2, we have probability of A1 union A2 is equal to probability of A1 plus probability of A2 minus probability of A intersection A2. This is addition theorem on probability for 2 events. Let us suppose that the theorem is true for n is equal to r. Just replace in this expression, instead of n, r, I is equal to 1 to r ai. This is summation of single terms, double terms, triple terms, and last term up to r. Up to r. Look here, up to r. Now we have to prove it for n is equal to r plus 1. Okay. Probability of union I is equal to 1 to r plus 1, ai is equal to, we know that this is I is equal to 1 to r ai. Union, this can be written as union a r plus 1. Again this is a1 and a2. This is union of 2 terms. Apply probability, addition theorem on probability for 2 events. Probability of this first term union I is equal to 1 to r ai, probability of second term a r plus 1 minus probability of union of this term, first term, intersection a r plus 1 from addition theorem on probability for 2 events. Look here, I just expanded this term only. These 2 terms remains same. Here this is a1 intersection ar plus 1 union a2 intersection ar plus 1 union so on r times ar intersection ar plus 1. So instead of this, this is the union of ai intersection ar plus 1 terms union up to r terms. So we can write this as, this is first term up to r, this is second term, again we have 3 terms, the last term a r minus 1, a1 intersection a2 intersection ar plus ar plus 1. This is up to this, we have union of I is equal to 1 to r. This is from equation 2 up to this. This is plus the second term a r plus 1 minus, we can write this as union of intersection terms up to r. This is from distributive law. This r plus 1 a r plus 1 and this I is equal to 1 to r ai summation I is equal to 1 to r plus 1 ai probability of ai. This is 2 terms, these 2 terms up to this, the r term minus, expand this, again expand this. This is union of ai intersection ar plus 1 r terms. So We apply addition theorem on probability for two events from 2. So up to this, no change. Here I is equal to 1 to R, first term, AI intersection AR plus 1, first term, minus two terms, AI intersection AR plus 1, AJ intersection AR plus 1, so on. This is summation of two terms. Similar to this. Instead of AI, we have AI intersection AR plus 1. Instead of AJ, we have AJ intersection AR plus 1. The third term is AK intersection AR plus 1, like that. But the second term is two terms only, minus A1 intersection AR plus 1 intersection A2. This is the last term. A probability of A1 intersection A2 similar to this is the last term. This is the R intersection terms. We have R intersection terms. Here we have R plus 1 also. So the first term is I is equal to 1 to R plus 1, and we have this is A I is equal to 1 to R, probability of A intersection AR plus 1 minus probability of I less than I1 is less than or equal to J less than or equal to R up to this is, instead of this second terms, up to R plus 1 we have these intersections, minus R plus 1 minus 1 we have up to R plus 1 minus 1 power R plus 1 minus 1. This is the last term, intersection terms up to R plus 1. Now I is equal to 1 to R plus 1, first term. This is up to R plus 1 terms. Look here, we have up to this is R plus 1 terms. R plus 1 terms, second term. This is R plus 1 terms, three terms, minus last term is up to R plus 1 intersection terms. So this theorem is true for R plus 1. Hence the theorem is true for n is equal to R plus 1 by mathematical induction. The theorem is true for all n events. From this lecture we have seen the simple theorems on probability, addition theorem on probability for two events, for three events, and for n events. Thank you.